Everyone. So in this video, we're going to talk about how to determine the strength of acids and bases. And I hope that in this time of digital learning and uncertainty about when we'll be back at school, I hope these videos are bringing you some sort of comfort, just in the fact that, we keep learning and it's still me teaching you. So with the strength of acids and bases, I kind of want to make sure that we touch back on something that we mentioned in the first video about conjugate acid and base partners. And something that I want to make sure that we talk about is that the conjugate partner, because remember, conjugate means partner. So the conjugate partner will always be the opposite in strength of the original acid or base. So for example, if we look at HNO3, we know that this is an acid because it starts with hydrogen. So this is our acid, which means whatever it produces after it donates that hydrogen would be our conjugate base. So I'm just going to abbreviate that as CB. So we know that when HNO3 donates its hydrogen or its proton, it would become NO3 with a negative charge. So if this would be considered a strong acid, this is a weak base. Ammonia is considered a weak base, relatively, and so when it accepts a proton or a hydrogen and becomes NH4 positive, it would be a strong acid. But I want to keep in mind that it's not necessarily that it's a strong acid, it's just that it is a stronger acid than NH3 is a base. It's just, a stronger than its counterpart. Or in the case of nitrate, a weaker base relative to the strength of nitric acid. Nitric acid as its acid. Hopefully that makes sense to you. So what I want to look at first, though, is this picture of acid-base acid strength and conductivity. You should have learned about this a little bit when we did our kind of exploring using the PhET simulation on Monday of this week. However, just in case you didn't get to it or you're watching these videos ahead of time, one thing to keep in mind, so HCl, hydrochloric acid, is considered a strong acid. And so what you see is that when hydrochloric acid is mixed with water as a gas, that means it's dissociating. What happens is the hydrogen from HCl is donated to the water to form H3O+, which is our hydronium ion. Oftentimes it's abbreviated as just H+, but that is our hydronium, and then we have chlorine left over, so it's dissociating, and what you can see is that literally all of these HCl molecules, you can see the chlorine is the big gray one, and the hydrogen is the little one there, they're all breaking apart. So you see all these negative and positive charges. So you see this 100% dissociation. So it's breaking up like every single every single hydrochloric acid molecule is breaking up. You can also see their image of a conductivity meter here, and the fact that these lines are pretty long means that the conductivity meter is bright, meaning the light bulb is lighting up, so it's a strong electrolyte. Whereas if you look at hydrofluoric acid, which is a weak acid, when it is put into water, it is also going to dissociate. It's going to donate its hydrogen to water to form the hydronium ion, which remember, hydronium is spelled like this. So it forms our hydronium ion and fluorine with a -1 charge, but notice you only see like a few of the negatives and positive charges, so like 2 out of the 10 that they put in there. So you only see about 20% dissociation, and that dissociation is really what makes something strong versus weak. the reason why is when it 100% dissociates, this hydronium ion concentration is going to be a lot higher, which means it's going to have an extremely low pH relative to this hydrofluoric acid, which only dissociates by 20%, and the hydronium ion concentration will not be as low. But again, that assumes that you start with the same amount to begin with. If you change the amount of those, then the pH and the relative strength of the whole solution as a total can change. So, all right, let's zoom back out and look at this next thing. So the next couple of parts of this video are really going to be more of like going through questions and looking at how you might be asked questions about them and how to explain them. So one thing that would be really good is for you to pause the video and maybe attempt filling out this chart and answering these 3 questions on your own. So go ahead, pause the video, try to work them out and see what you can do, and then press play when you're ready to resume. Okay, so one thing to notice is that we have the hydrochloric acid that we mentioned earlier and the hydrofluoric acid, but we have different concentrations. A and B are both 0.06 molar, whereas C and D are both 0.03 molar, which means that C and D have half the concentration, or half the number of moles, that A and B do, which you can tell by their initial number of acid molecules. Now, when we are calculating percent dissociation, it's the molecules reacted divided by the initial number of molecules, or the number of molecules that have dissociated divided by the initial number of molecules. And so for B, that would be 8 divided by 40, which to get its official percent ionization, you would just multiply that by 100. And 8 divided by 40 times 100 will give you 20%. But when we look at C and D, here we have 20 molecules react out of 20, which is again 100%. And for D, it's 4 divided by 20 times 100, which will give us 20%. So you can see that the dissociation here for both hydrofluoric acid and hydrochloric acid stay the same no matter the concentration. Like, it doesn't matter if you have 1 molar or 12 molar, it's still 100% ionization or dissociation. And so we completed the table in number 1, and they said to describe the relationship between the percent ionization of the acid and the conductivity of the solution. And so using this, which is Model 2 and Model 1 being our picture, they said to compare it to the conductivity. So we can say, well, that so the higher the percent ionization, the more conductive it is. And that's because ions are used to conduct electricity. Like, they're able to hold those extra electrons when you have all those extra positive charges in the solution. And so the more ions you have, the more conductive it is. And number 2 says, is HCl a strong acid or a weak acid? And we know that it's a strong acid. 1, it labeled it here, and we can see its conductivity meter is bright, but we know it's a strong acid because it 100% dissociates. So remember, whenever you're answering a question with science, you want to have like your claim, and then you want to have your evidence and your reasoning. So is HCl a strong or weak acid? Our claim would be HCl is a strong acid. And then if we wanted to cite our evidence, which you know I'm always asking you to cite evidence and things like that, in Model 2, the percent dissociation is 100% compared to HF's 20%. This means HCl is a strong acid because the H plus concentration will be greater. So that's a little bit longer than I had space for, and probably a little longer than you needed, but I wanted to take the opportunity to make sure that we understood our claim, evidence, and reasoning, just making sure we're explaining the evidence and what that means. And so here we can do the same thing, but maybe not as long. We're just going to say that HF is a weak acid because it only dissociates 20%. And another type of problem, and again, remember, these problems are literally just because you're going to have a test on them. Even though we're digitally learning, you will still have a test. So just kind of making sure we understand how to answer these kind of questions. So in this problem, I had a little bit of a typo here. And that should say acid. Okay, so list from weakest to strongest, and so we're gonna be looking at acids with there, and it said to look at pH first and then molarity. So one thing you want to remember is pH can tell us a couple of things. So if we're looking at pH, we know that the pH kind of goes from 1 to 14 with 7 in the middle, and we have acids below 7 and bases above 7. Well, if I want to know the weakest to strongest acid, the closer I am to 1, the stronger the acid is. If I was close to 14, I would be a very, very strong base, but a weak acid. So when I look at my pHs, 9s are more on the basic side, which means extremely weak acids because they're actually moving into stronger and stronger base territory. So the pH of 6 are actually the only two that are in the pH range for an acid. And so when I look at this, we then want to look at the concentration. So you would think that 3 molar, because 3 is a bigger number, that would make it the strongest, right? But something that is 1 molar, meaning it only has 1 mole of its acid, whereas acid number 4 has 3 moles of its acid for every liter, can produce the same effect. So solution acid number 2 needs less numbers of moles to get the same pH or the same hydronium ion concentration, which means that acid number 2 is actually going to be our strongest, and acid number 4 is going to be the next strongest because it needs 3 times the amount in order to have the same effect. And so then when we look at our absolute weakest, we can see with a pH of 9, those are going to be our weakest, and we look at 1 molar and 3 molar. Again, 1 molar is going to need only 1 of the amount, or like 3 molar needs 3 times the amount that 1 molar does to have the same effect. And so with that in mind, that means our acid number 1 is going to be the next weakest, and acid number 3 is going to be our actual weakest one, because it requires 3 times the amount of hydronium ions to still have a basic pH and not even a weak acid pH. Now, number 2 says if substance A has a 56% dissociation and substance B has a 78% dissociation, which one is stronger? It has to be substance B because it has a higher percent dissociation, which we probably should have written down as I was talking. So substance B is stronger because it has a higher dissociation. Sorry for the bad handwriting, everyone. If I had written that on the board, y'all would have been like, Miss, what letters are those? So hopefully you can tell. With the rest of these guys, I'm just going to kind of skip through some of them, but you can always pause the video and do the ones that you don't know. I'll kind of put the answers for them and you can look at them and see if you can figure it out. So for number 3, I'm not going to work it out, but it would be 56%. If we have an ion, because it's an acid, the ion that forms, okay, in number 3, it's talking about a hydroxide ion, but it's talking about a base. If this was an acid, it would be an H+, or a correct answer would be hydronium ion. Now, with hydronium ions and the pH scale, kind of what we said earlier, just remember this from a previous video. Changing pH of 1 is actually an increase by a factor of 10. So if I go from a pH of 4 to a pH of 1, we would say that a pH of 1 is 1,000 times stronger than a pH of 4, and that's because it moved 3 times. So that's saying 10 times 10 times 10, which gives us 1,000. You can kind of answer these on your own. You should know acid, base. For number 3, you should get 100 times. For number 4, which again, pause the video if you're trying to do these on your own. Number 4, you should say that it increases by 1,000%, and it's definitely becoming more acidic because it's lowering its pH. So for number 6, I will actually walk you through this question. So it says a student dilutes 10 milliliters of 1 molar, that shouldn't say NaCl, that should say HCl. So 10 milliliters of 1 molar hydrochloric acid using water. If the original solution had a pH of 13, what would be the most likely final pH of the solution? Now, remember that when something is being diluted, that means it's probably had extra water added to it, and you're decreasing the concentration of the hydrochloric acid in there. Meaning for every hydrochloric acid molecule, you have a lot more water molecules, so it's making the overall solution weaker. Now, when you dilute something, and this is going to be kind of a really important side note, diluting moves pH to 7. So if you have, for example, on your pH scale from 1 to 14 and 7 is in the middle, if you have an acid that's down here and you dilute it, it's going to move towards 7. If you have a base that's, I don't know, 13 or 14 and you dilute it, it's going to move towards 7. Either way, because water has a pH of 7, so it kind of moves it closer to that. The more water you add, the more it will move towards 7. So in this case, because it has a pH of 13, we know that it's going to move closer to 7, which means it's going to decrease. Now, we can also see that all of our options, A, B, C, and D, have decreased. C is not an possible answer because -4 pH, not going to be our thing. Although technically I have seen something with a -1, but there's no way that adding water is going to make something jump from positive or from a pH of 13 to below 7, which is also why a pH of 2 is also not an option. That would be an extremely strong acid. Adding water does not do that to something. Now 7 is a possibility because that's where water is and it's neutral, but keep in mind that our pH is 13 and they're saying they're diluting it, but they don't say they're diluting it a whole lot, which means that D is most likely what it is. If in order for it to go from 13 to 11, they would probably have to increase the volume from 10 milliliters to about 1,000 milliliters, and again it would only drop the pH by about 2 because of that change in concentration. So hopefully this video helps and kind of gives you an idea of some practical questions that you could be asked on a quiz or test.